Hello, everyone, and welcome to European Sustainable Energy Week. So today we are actually having a hybrid online event and in person at the same time with the session for unlocking geothermal energy. And we will be discussing process, technologies, and opportunities. And we are now in Manchester and at the same time joining you online. So what is the European Sustainable Energy Week? Basically, the whole idea revolves around a clean, secure, and competitive energy union. That's what is going to be achieved through the European Sustainable Energy Week, through different talks, discussions, and what we are going to be starting today as the first event. And it is actually the biggest annual event dedicated to renewable and efficient energy use in Europe. So it will be a series of events, a 3-day policy conference, the award ceremony and energy fair, and we have begun by the event, I would say, with our unlocking geothermal energy section. So we are going to be starting today, me being the moderator, and then 3 of my good colleagues that you see on the screen, Tuğrul Hazar, Kevin, and Mahfuza. They will be basically giving different presentations. I will go through the details in the next slides, but you can see our pictures. So this is me, Kevin, Mahfuza, and Tuğrul. We will be trying to basically discuss a lot about how geothermal energy can unlock the potential for renewable as a renewable energy resource. So this is me. I basically work at Fraunhofer IEG, and I'm responsible for a competence center for monitoring and AI, and I will be moderating the session today. As the next speaker, we have Tuğrul Hazar. He's the assistant manager at Zorlu Energy Group, and he will be basically discussing and presenting to you the geothermal energy systems in general, the features, scopes, and how it can be considered as a sustainable energy resource. At the next step, within the next presentation, we will have J Mallin. He is the managing director at Geolorn Ltd, and the topic that he will be discussing would be drilling techniques in geothermal energy systems, and basically that would be the drilling technologies and reservoir accessing technologies, or how can we access the reservoirs in an efficient manner. And then as the next step and the last one, we will be basically being presented by tools and innovations for geothermal energy harvest. How can we do that? What are the innovative parts? And that will be basically presented by Dr. Mahfuza Ahmed. She will be the last one, and she's a collaborative research leader at the company TBS, which is actually hosting us today for this event. So as a wrap up for the introduction, so we are part of an EU Horizon project called nGEL, and as the next step, I will briefly give an overview about the nGEL project, which is related to the geothermal energy, and afterwards we will continue with the main presentations. So to just very briefly and shortly give an idea about the nGEL project, nGEL stands for Next Generation Flexible Tri-Generation Geothermal ORC power plant. And it's part of innovating geothermal energy for a carbon neutral Europe. But I will give you more information, just a project overview. So we are relatively a small consortium consisting of actually 8 partners, 7 officially. We have 2 Fraunhofer institutions, TBS, Zorlu Energy, Geolorn, Vito, REPG, and Naldio. So the project is basically going to be running for 48 months, and we are in the middle of the project duration. So we are more or less at half. We have 3 main technologies or key technologies that we are developing, and within the course of the project, we have 6 milestones, main milestones to achieve, to basically achieve the main goal, which I will be discussing right now. So the core mission that we have within the project is to transfer geothermal ORC power plants, instead of just producing electricity, into a flexible tri-generation system that would be basically producing electricity, heating, and cooling at the same time. And how we are going to do that through multiple different technologies, but mainly also through an AI-based energy management system. So just to give you an overview, heating and cooling accounts for basically 46 or almost half of energy consumption in the EU, but only 18% is met by renewables. So basically considering these numbers, nGEL and a lot of other projects, specifically nGEL with the tri-generational aspect, we are trying to basically target this untapped potential, specifically for low to medium temperature geothermal resources. And as the next step, just going bigger within the picture, then we have estimated that if we can apply the nGEL technology across the EU, then we would be meeting roughly around 4% of the EU clearance annual heat demand, which would be roundabout savings of roundabout 10 billion euros annually. So we are aiming for a great impact and we want to really achieve it, but there are multiple challenges on the way. The energy consumption gaps. So as I just told you before, I don't want to be redundant about it. 46% of the EU energy use is heating and cooling, but it's not being produced by the renewables. There is a lot of resilience on the fossil fuels, and there are instability within the grid when we are using renewables and at the same time low temperature resources. It's underutilized, especially using the ORC plants. So what do we need based on the challenges that the EU is facing at the moment is to have, as the name of the project also suggests, flexible and scalable renewable energy systems, which is what we are trying to achieve through the tri-generational system. At the same time, when you have the grid instability, we need real-time demand response, and that's where the AI and the EMS, our intelligent EMS, is coming into the picture, trying to basically address that challenge. And at the same time, it's the low temperature resources, as I just was mentioning, is underutilized. And what we are trying to do is basically achieve scalability across the EU by targeting also the sedimentary formations. So about the key technologies, I will be trying to go for a fast overview over it. Like, we want, or we have already almost designed the flexible geothermal ORC with the tri-generational capabilities, heating, cooling, and electricity production. Then we want to basically have the demand side management, as I was mentioning before, to overcome the challenges, and then by doing that, increase reliability of the ORC plants against the high ambient temperatures, which we may hear about probably in the innovation part at the last presentation. And bringing these together, we will have an energy management system for the flexible ORC at this point. Then we will integrate that through a digital twin into the ORC plant, and to bring in all these together, an additional design and development for a cold thermal energy storage technology will be done to basically address the cooling aspect. So there is a heating, there is electricity production, but we are also addressing the cold thermal energy storage systems. And we want to do that as a wrap up to ensure environmental sustainability, to bring sustainability into the picture. The solutions, just to summarize what I was discussing before, there will be the AI-driven energy management system, the hot and cold thermal energy storages, and also usage of absorption chiller and heat exchangers to support the second aspect. So the key innovations basically would be the digital twin, bringing all our digital innovations together while having demand side management. That would be basically the adaptive control strategies. Just as an example, if the demand for electricity is lower at a point in time, then the electricity or the surplus of the brine can be used to produce heat or cold and store it and use it when it's needed. But we will be hearing about that in the next presentations. By doing that, we will enhance the resilience and we will have smart control integration to achieve all this in an intelligent and controlled environment. So we are having a pilot and we are aiming for TRS 7 to 8 for this project. And the target pilot region is actually one of the biggest geothermal power plants in the continent, and that's basically the Cathedral region, and that's where we are going to be doing the demonstrations for the technology. And the goal is to, at the same time, after the demonstration, to test the scalability, optimize the energy management system, and evaluate what would be the environmental and economic impacts. And at the same time, we are doing community engagements to understand what would be the local providers and at the same time people requirements regarding integration of such technologies. So I will try to wrap up here. it would be great for you guys to join us. We are very active on social media, and at the same time, we have a lot of newsletters and announcements that we do. So please scan the QR codes or make a picture, and it would be really great to basically get connected, and then we can follow up and probably even do collaborations together. So now I will give the floor to my good colleague Tuğrul Hazar, and then he will be.
Now I'll go into detail about more about the geothermal energy in general, and then what we are going to be doing in our project in the nGEL as an innovation part. So let me just reintroduce myself. My name is Tuğrul. I work in Zorlu Energy as R&D assistant manager. I have my background in mechanical engineering, and I have been working in Zorlu Energy for about 5 years now. And without further ado, let's talk about what is the geothermal energy. Well, the geothermal energy is the heat energy of the Earth itself. Its main sources are the radioactive decay on the outer surfaces, outer layers of the Earth, but mainly the mantle and the core's heat energy, which was caused by astronomical events a couple of billions years ago and still has its heat present for our use. And this thermal energy is mostly stored in rocks and fluids in geological formations, which we call them reservoirs if you are going to tap into them. And as power plant operators or district heating operators that utilize the geothermal energy, we tap into these reservoirs and we try to extract the heat by means of utilizing geothermal wells, production and injection. And the difference between the inner layers of the Earth and the outer layers causes that continuous heat induction from inner to outer exterior parts of the Earth, which helps us replenish our heat sources in the geothermal reservoirs. And let's take a look at the world situation in geothermal energy, and then we'll go a bit lower scale into Europe, and then we'll talk about the different methods of power generation from geothermal. So right now, I think this is 2024, we have 17,173 megawatts installed capacity electric in the world, and about 1/5 of it is stated in Europe in 2024. 3,500 megawatts electricity is installed capacity we have in geothermal sector in Europe. However, we have a much higher potential of geothermal. So we're planning to utilize this energy, and in about 2032, we're planning to double the amount we have right now in terms of electricity, but we are also utilizing a lot of geothermal energy in district heating. You can see the orange lines representing the district heating and the blue lines representing the power generation throughout Europe. So let's talk about how it's utilized in our day-to-day world, day-to-day life. So most of the geothermal energy is used in heating or cooling or power generation. But additionally, we are using this energy in food drying and then thermal tourism and geothermal mining as well. And as of last couple of years, there's an emerging technology called sustainable aviation fuel or green hydrogen, where we utilize green or renewable energy plants to generate some materials or some fuels that we can use sustainably for our vehicles, like jet fuels or vehicle fuels, which will help create secondary revenues and more investments, hopefully, in geothermal sector. So let's talk about the geothermal power plants and how they work. As in conventional Rankine cycles, we use a boiler, a pump, a turbine, and a condenser to create a full cycle and generate some power. In geothermal energy, the Earth itself, as we explained before, acts as the pump and the boiler, as we don't need a fuel to burn to create heat. We already have the heat in geothermal energy. So depending on the temperatures and enthalpy levels and the fluid types, or if there is any fluid in the reservoir, and the overall formation of the soil, we can decide which type of power plant, or if we are going to use a power plant at all in geothermal energy. If we have high temperatures, as you can see from the table, if we have high temperatures above 150 Celsius degrees, and we have water or steam dominated reservoirs, that means we can either use dry steam, flash cycle, or combining them together and create a combined cycle geothermal power plants. If we have medium temperature reservoirs, which is between 90 Celsius degrees to 150 Celsius degrees, which we most commonly have in Central Europe and some part of the Eastern Europe, then we can, if we have the fluid type as water, if it's water dominated, we can use binary organic cycles, and in sometimes we may even use flash cycles if we are on the higher levels of this range. And if we have lower temperatures below 90 Celsius degrees, that means we cannot boil the water by its own means, which means we will have to go for a binary use or a heat pump, or we can directly use this heat for district heating or greenhouse heating purposes. But either case, we will be requiring some media, such as fluid, that we can use like water or steam, or maybe we have to create our own media, such as creating a doublets or closed loop cycles to extract this heat from the reservoir. So let's talk about the dry steam power plants. In dry steam power plants, the fluid is mostly liquid in the reservoir, but as the fluid comes up the reservoir, the liquid form, the pressure drops, of course, and as the pressure drops, the boiling point is also set on lower levels. That causes the complete liquid to flash into steam without any liquid present. And this steam directly goes into turbine. Maybe a small demister equipment is used to remove the suspending liquids inside the steam to prevent any damage happening to turbine blades. After the turbine, these low enthalpy steam is then condensed into cooled water and re-injected back into the reservoir. These concepts do not change in any geothermal power plant operation. The production well and injection well acts the same way. The media might differ in terms of fluid, steam, or gas, but the operation method is almost the same. And you have to re-inject when it's in liquid form to prevent excess amount of power consumption and then a controllable injection. And then comes in flash steam power plants. This is utilized when you have enough enthalpy for the steam to be generated, but also you have some liquid also existing in the mixture. That means you have to separate the steam from the liquid, but to do it in an efficient manner, we utilize a control valve before the separator tank or the flash tank in it, as you can see in the diagram. Before the flash tank, we set the pressure to a lower level than the fluid's own pressure, so we create even more steam to utilize in our turbines. And then we mix this, after we condense this steam, we mix this with the liquid part of the geothermal brine. And I'm not sure if I mentioned this, but the fluid we call in geothermal is mostly named brine in terminology. So this brine is mixed with the condensed steam, which is liquid again, and then re-injected back into the reservoir. And the last one, where we have mostly low enthalpy reservoir or low enthalpy fluid from the reservoir, or we have low amounts of flow from the reservoir, we utilize binary cycles. Binary cycles, by its own definition, means two different cycles. We have the brine cycle that comes from the reservoir, is not turning into steam, maybe even small amounts, traceable amounts, but they do not affect the overall design. They are usually separated and removed from the system, so they don't cause any inefficiencies in the heat exchanger, and then condensed and again mixed with the brine itself for re-injection. That's our primary line. And then we have the secondary line, where we utilize an organic Rankine fluid, such as ethane or butane or isobutane, a similar fluid, where we have a lower boiling point and lower condensing points, which can be efficiently used for power generation since it's in the range of our temperature. So we have some complex systems such as combined cycle in geothermal power plants. These combined cycles can differ in terms of design, but as you can see, this is one of the designs that we are using right now in Kızılderili 2 geothermal power plant. In this one, we are using consecutive flashing. So we have high pressure, intermediate pressure, and low pressure separator. After each separation process, the liquid still has a lot of enthalpy, a lot of steam potential. So we are continuously decreasing the flashing set pressure starting from 7 bars, going down as low as 1.1, 1.15 bars. And we are getting different amounts of steam from each separation process. And we are utilizing this steam in the corresponding turbine inlets. And after the operation, we are reinjecting the remaining brine. However, as you can see on the top side of the top right side of the diagram, after the HP high pressure steam is utilized, it still has a lot of energy. It's not called energy, but it's called exergy, a usable energy. So this energy can be utilized somewhere else. And in our design, we are using it to create even more energy by transferring the heat from the high pressure waste steam to organic Rankine fluid to generate an organic Rankine fluid steam and generating more power from that cycle as well. All right, so there are some advantages and disadvantages of using a dry steam, flash cycle, or binary cycle power plants. One of the highest efficient part of the flash steam, dry steam, or combined cycle geothermal power plants is that you have abundant amounts of liquid, which means you can condense some of the steam into water, and without needing any makeup water, you can utilize a cooling tower, an evaporative type cooling tower, where you can efficiently cool down your internally used cooling water, where you utilize this water in IP or LP condensers or in the condensers of the binary cycles. However, if you're utilizing only a binary cycle power plant, you have to utilize the municipality water or municipality brine water to continuously make up for the water that you would lose in the cooling towers. That's why the binary cycles are mostly utilizing air chilled condensers, ACCs, which are efficient in terms of visibility. However, they are really inefficient when it comes to stable power production throughout the whole seasons. In summer months, the effective power drops down to around 50-55% of the installed capacity, which is quite inefficient for a base load renewable power, which is the only type in the world. Geothermal is the only base load power that the main resource is renewable. And that would create a problem for the ORC power plant operators, because since most of the Europe do not utilize a flash cycle, only Iceland, Italy, and some parts of the Western and Southern Europe can utilize flash cycles or dry steam cycles. But most of the Europe utilizes an ORC cycle. And inefficiency in the ORC cycle causes the investors to be unsure or reluctant about their investment. So the main focus should be, as nGEL, that's one of our main focus as well, to increase the overall efficiency of the ORC power plants. As you can see, this is the initial design that we had during our proposal stage of the project for the nGEL. We have 2 demo cases. One demo case is focusing on the tri-generation abilities or flexibility abilities of the geothermal power plants, and demo case 2, which focuses on the overall efficiency increase in the ORC power plants. As you can see, in day-to-day operation in a geothermal power plant, the prices of the electricity can differ from day to day or throughout the day itself. It can fluctuate, and causing the investor to be unsure, cannot have a forecast on when the return of investment could happen. But if a geothermal power plant had the flexible ability to change its main course of revenue at the time, such as heating, cooling, or extra power generation with the help of the power storage or thermal energy storage, the story might be a lot different than it is today. So as you can see, we considered some cases, some base cases, and throughout the project, we will be working on them even in more detail. But our main idea is that when the power prices are lower on the electricity market, then we can divert some of our fluid for either heating, if it's the colder months or colder seasons, or heating or cooling, if it's the hotter seasons, or storing the energy in a thermal energy storage tank to be utilized later on with the help of a secondary ORC or smaller additional power. Even without the secondary ORC, in geothermal power plants, while it's a base load, sometimes the power cannot be matching the installed capacity. The effective power cannot be matching the installed capacity, since there are some drops in pressures or temperatures in the reservoirs throughout some seasons, and you cannot reach your installed capacity. But if you had an additional heat load, heat resource, such as a TES in this case, you could utilize this additional heat to almost match the installed capacity coefficient. So let's see it in more detail now. This is the final version which we'll be working on in the nGEL project. As you can see, we are utilizing thermal energy storage tank. You can see in the middle. We are utilizing absorption chiller for cooling purposes, where we will be using the main heat source as the let's call waste energy at that time, since we will not be getting any revenue from it. And we have also called thermal energy storage, where we can utilize it if it's not needed at that time, but can be used later on. We also have district heating option or greenhouse heating option when we have excess energy on the power generation part, but the power prices do not match our requirements. So we will be utilizing an EMS to help our partners EUSEW and Naldeo and Fraunhofer, of course, all together. We will be working on this one to actually autonomize the system, and without the interference of human, it can actually decide from the forecast of the ambient temperatures, of the power markets, the merchant prices of the electricity, and it can decide for us, for the operators, when it makes more sense to generate power, store power, generate heat, or generate cooling. So that's the main idea and the main innovations that we want to achieve, or the main objective we want to achieve in nGEL project. And without any further delay, I'd like to leave the floor to my beloved colleague, Kevin. Thank you.
Thank you, Tuğrul. That's very interesting. You click on.
Yeah, I think they're right.
Cut upside down.
This one. Yeah. There you go.
Okay. As Tuğrul mentioned in his early slide, all of this geothermal energy and resource is buried. It's below us. It's like somebody, when they were designing the Earth, decided, let's put in underfloor heating. And we're suddenly in the 21st century thinking, this is a good idea, isn't it? Let's try and use it. What I'm going to talk to you about today is how we access into these geothermal reservoirs or high temperature rocks, and how we utilize that heat at the surface, which ties in with Tuğrul's presentation. I want to be honest, this is going to be an overview, and we haven't really changed the way we've drilled things for over 100 years. We're still basically imparting mechanical energy into the formations to break them up and then move them out of the hole. So all of you who have put up picture frames on your walls at home or whatever and need to drill a screw in, that's the basic technology we're using in a slightly larger way. The key thing we always talk about, if we're going to spend money on drilling, we want something at the end of all the work we do. We need a wellbore that is usable. So quite often we'll talk about, oh, let's drill really quickly. But if you spend half the amount of time to drill a hole that you can't use it, you've wasted all that time. So we're looking at having a usable wellbore, because that's our access to the resource. The main drilling technologies used today, and they're still in use today. I mean, there's a few exotic versions of them, and I'll talk to you about those in a minute. But we have rotary percussion, which is basically the same as your little handheld hammer drill at home, which is powered by air generally. There are fluid-powered hammers, and these are increasing in their technical capabilities. We have roller cones, You'll see these in a minute. And then we have fixed cutter bits. So those are the basic technologies in use today to make a hole in the ground. Down the hole hammers is probably the biggest market for drilling into rocks. They're very efficient. They're very expensive to operate because, to compress air to the pressures that we need and the volumes that we require is quite expensive. So we're looking at alternative methodologies now to still have the same sort of level of impact to break rock, but at a slightly less energy intensive way of doing it. And when we look at the overall cost of drilling, we try to analyze specific mechanical energy. So how much energy do we have to use to break the rock and then move it out of the hole? So it's quite a technical subject and probably not for today, but for those of you who are interested, reach out to us because we can, we're very happy to share all this information and a lot of the new technology that are coming along. I just wanted to say as well, I love the fact the European Union has started to call this sustainable energy. For too long now, we called it renewable, and lots of people think, we don't need to do anything. It's renewable energy. What we need is sustainable energy, whether it be renewable or from other sources. So sustainable is very much in the focus of what we're trying to do here, is get slightly more out than we put in. These are down the hole hammer bits. You'll see there's what we call the bit bodies. On the left, you'll see blank sort of circles. That's where we put the inserts. The one on the middle, you'll see where we put the inserts, and then the one on the right, where we got different holes for flushing. We designed these bits to match the rock types that we're drilling. Okay, so if we have a very hard rock, we'll have a small rounded button. If we have a softer rock, then we use what we call an impact bit. These are, let's say, for a 200 mil bit, that you're going to be paying around 1,500 euros for a bit. These are compression systems. In that container on the top there's two compressors contained in there. That puts out around 60 cubic meters a minute of air at around 35 bar. So there's a lot of air and a lot of pressure. Below, the yellow contraption, which looks like an old car engine, is in fact what we call a booster. That takes the air from the compressor, it recompresses it again, and we can run those up to the most we've seen is about 500 bar, so 7,000 psi. It's a lot of air and under high pressure. So there are risks associated with using these technologies. But the one nice thing is, because it's compressed air, we never run out of feedstock. If we run out of air, then everyone's on site dead, so it doesn't matter. This is the same version, but here we use high pressure water or some other fluids, but generally water, and we pump the water under around 250 bar through, and we have a hammer cycling here. Shahin and myself and our friends at TVS were involved in a project in developing a more efficient version of this water hammer, which is not quite so affected by reground cuttings going back through the piston. But it works the same in basic terms as the air hammer, but uses water. The advantage with that is the hole velocity of your flushing fluid is much lower than it is with air. So you get less wellbore damage. And under high heads of water, so if you drill into an aquifer that's, you know, quite high water heads, we can keep going. Whereas with air, we have to make sure we have enough air pressure to aerate the water to lift it out the hole. So that becomes a limitation. These are one of the more new exotic versions of a water hammer. I put this up here because I'm a shareholder in the company. It's a great step forward. It uses a dual circulation system, so we can put dirty water down for flushing and separate the clean water for cycling the piston. It's not cheap system, but it is, you know, on a cost benefit analysis, you can drill quite deep at, you know, very high rates of penetration. And ROP is what we tend to look at. So the rate of penetration is how we work out the overall cost, because if you're drilling quicker, then you're getting your return on investment that much quicker. Generally, if we stay in the higher strength rocks, which a lot of geothermal is looking at now, you know, we're getting about, with conventional drilling, we're getting about 5 meters an hour. With hammer drilling, we're getting around 15 to 20 meters an hour. So with the, you know, it's a market increase in using down the hole hammers. These are sort of percussion enhanced rotary drilling. It's a technology that's still in its infancy, but it's basically using a standard rotary drilling bit, but there's a piston inside that long body that you see, which adds impact energy to the bit. We had for a long time been doing this in the mining industry, and it's called percussion assisted rotary drilling. It has its benefits and it has its drawbacks. And there's a sort of this is from the company that made these things, you know, what they've done there in granites. These pictures are probably something that most people know. You've probably seen it on Armageddon with Bruce Willis, you know, sort of chomping away at a meteorite and trying to stop it hitting Earth. This was invented by Howard Hughes and his good friend in Bakersfield back in the 1920s, 30s. I can't honestly remember. And we are still, majority of deep wells are still used these bits. They're good because there's a lot of history behind them. So to just completely dismiss rotary drilling is rather foolish, because when you look at probably 95% of all deep holes that have been drilled with this methodology. So it's proven. It may be slow, it may be outdated, but it's proven. So we don't want to throw these on the scrap heap just yet, because the people, like companies like Baker Hughes, are still developing different types of inserts and all sorts of gauge angles, etc. So I think it'll be another 10, 15 years before we see the complete demise of the roller cone. When it's first invented, it only had 2 cones, but then it didn't really ring true like dicone. So Howard put a 3rd one on and called it tricone. Sounds a bit better. These are what we call fixed cutter bits. In the old days, we only drilled soft formation with these. So say like mudstones and weak shales and softer limestones. Over the past sort of 5, maybe 7 years, people have been experimenting by using these in hard rocks. And in hard rocks, I mean things like granites. Everybody knows that granite is really hard. And we're getting some incredible results from this type of bit. It requires a lot of, again, a lot of specific mechanical energy to break rock with these. And these bits are expensive. A 200mm bit in this type of format would cost you probably $60,000 to $70,000. So there's you've got to do the cost benefit analysis of making sure that running this bit is commercially viable for you. So they also, it requires a bit more skill to use these bits properly than it does with the downhole hammer. So your drill team needs to be a little bit more knowledgeable. But as I say, the companies like Zerdalab, and again, I put them up there because I do a lot of work with them. They, you know, they've got a really fabulous product. They design, similar to the downhole hammer bits, they will design a solution to match your wellbore. And that gives you a really great advantage. There's that says it all. They have an average ROP there of 13.86 meters per hour. They were drilling directionally, so that's when we go away from the vertical wellbore and we sort of track it to one side, which is becoming again increasingly common as we try to extend into the reservoirs in a greater depth. This is a rotary steerable system. This is again, this is probably over the last 5 or 6 years, this has become a sort of viable technology. Still very expensive, but it allows the driller to basically steer the bit wherever he wants it to go. He'll know exactly where it is all the time relative to where he is on the surface. And through very clever mechanisms inside the bit, inside the bottom hole assembly, he can rotate and steer this bit, change it to go left, go right, go up, go down, getting a signal to say, shut up, Kevin, it's time is up. But again, these are going to make the sort of our industry sit up and people be able to access things in greater depth. And there's a close-up picture of it there. And again, they're using the fixed cutter bit. I just want to quickly touch on where the more exotic research is going at the moment, and non-mechanical technologies are where we don't engage with the actual rock itself, but we're using energy to break the rock, and in some cases actually vaporize the rock. So we put high temperatures in there and vaporize the rock. Those are the sort of main ones that are sort of looking at, that people are looking at the moment, and I'll quickly touch on them. Electropulse boring, I put up there. You can go and look at these yourselves because they are very complex, to say the least. Plasma technology, there's a company called GA Drilling, which stands for Geothermal Anywhere. They've been developing the plasma technology for a few years now. Again, this is where they actually vaporize the rock. This is a very interesting one. This is Quasar Energy. They're using millimeter waves, again, to sort of break and vaporize and spallate the rock. They claim they're going to be drilling 20 kilometers in 100 days. So that's going to put us into the super high temperatures. And Tuğrul mentioned sort of 150, we're talking 550 to 750 degrees with these sorts of depths. And then laser drilling. I'll put a few more photos up here, or slides, because I was involved in a project that's just finished looking at how we can utilize lasers to drill to great depths. We've got a long way to go, but it is promising. And that's it. If we didn't fall asleep, and over to our good friend Mahfuza.
Actually,
Thank you so much, Kevin.
before Mahfuza, I'd like to add one more drilling method to the, because we've been working on a different project called deep lights. And yeah, in deep light project, we're trying to drill with the help of the pulse power. So we're using pulse power.
That's the first technology.
That's ECB.
Yeah, a different method. I know it's a similar method, but it's a
Yeah. And then there's the 500 as well.
Yeah.
People listening.
thank you.
Thank you, Kevin. So I'll talk about just briefly about tools and innovation for geothermal energy harvest. So we all know geothermal energy is the most reliable, sustainable, and it's a renewable source of energy. And as you can see from the plot, that the availability factor for the geothermal energy is the highest among all others, renewable energy. And and it is as well for the other fossil fuel energy as well. And the capacity factor of the geothermal energy, as you can see from the plot, that it is the second highest among all of the renewable energy. So it has lots of actually positive and favorable things to use it for the power development. And that's what we're saying, that it's growing. But the problem with the geothermal power plant is its low efficiency, low plant efficiency, compared to other renewable energy and fossil fuel energy. One of them is thermodynamic limits. So far, we were able to, the reservoir, already to mention about the reservoir, the temperature available for the plant, power plant is about 150 to 400 degrees Celsius. Whereas fossil fuel comparatively, you see the 500 to 1,000 degree, and also CSP, the concentrated solar plant, is also quite high, as same as the fossil fuel. So this is one of the reasons that the geothermal power plant can't compete with respect to efficiency with other renewable energy and fossil fuel. So the low plant efficiency, there is one of the reasons. There are many reasons. I have just listed a few of them here. One of the reasons is the reinjection temperature. As you know, that the geothermal brine, they have some compositions, various chemical elements such as sodium, potassium, etc., and silica as well. And depending on the geographical conditions, some of the production well brines, they contain silica, some of them contain calcite, something like that. And these are precipitated, mainly the silica. It's precipitated in the plant. Therefore, that causes the silica scaling with the equipment of the plant. And therefore, it is required for the plant to reinject the brine at a high temperature. And that prevents the full exploitation of available geothermal energy. And another one is the corrosion risk. And, geothermal brine is fluidic, and that causes material degradation in the plant equipment, such as heat exchanger, turbines, anywhere. And therefore needs regular cleaning and sometimes inhibited use, material replacement, and that increases the operation downtime and results in lowering the efficiency. These are the only few actually I have listed here. There are obviously many more associated with other like drillings, and there are many others. So with Technovative Solution actually developing the decision support system tool, to evaluate the sustainability of different geothermal project configurations and innovative technologies. And we also simulate and optimize the plant performance. So this basically we're analyzing the sustainability. That's why we're calling it sustainability tool as well. We Technovative Solutions actually work on different Horizon EU Horizon 2020 projects and EU Horizon Europe projects. As you can see, these are listed below. All of the Horizon 2020 project actually completed. And currently we are working on the Horizon Europe projects, and those are nGEL, Serene. I think Compass is recently completed. And this project actually addresses various issues such as scaling, corrosions, erosions, also heat transfer efficiency of the heat exchanger, and obviously improve the drilling technologies to reduce the cost. And as Tuğrul mentioned about the ACC-based water plant efficiency drop during summertime, that actually, that means that the ACC-based water is not generating same power around the year. There is a drop of power during the summertime. So there's a scope of development to increase the reliability on it. And also, obviously, converting the baseload to a flexibility. Because given the the intermittent source of energy like solar plant and wind power, they started to increase their contribution to the grid. Therefore, now it's time to optimize the geothermal plant as well, so that they can use their energy efficiently. And when the demand is high, they can provide more power, and when the demand is low, they can store the energy for further uses. So these are the reasons that actually some of them we have addressed in, we'll see some of the projects addresses these issues. That's why I just mentioned only those issues here. And I'm not going all of the projects. So for example, I'll show our DSS tool and its sustainability analysis for some of the projects. The GeoHex project actually working on the mainly to improve the heat exchanger performance by increasing the heat transfer coefficient using the anti-scaling, anti-corrosion, and high-performance heat exchanger materials. And the GeoSmart project, it uses thermal energy storage, scaling reduction system, and automatic cooling system to improve the efficiency of the power plant, also to make the conventional water plant to a flexible power plant. Not water for GeoSmart, it is actually the flush type. And that the engine project, which uses a test and thermal energy storage and portable thermal energy storage and absorption chilling. And engine project's aim is to convert the basic water into a tri-generation, flexible tri-generation plant. And also it will address the issues of ACC-based ORC due to ambient temperature. And Compass Effect actually project, it's just it's an innovative laser lighting technology. I'm not going to give it details because I will not show the details for this project. And Serene project, which is developing electrothermal energy storage. Okay, so let's move on to the next slide. Let me see a cup of a bit of water. Sorry about that. Excuse me. So I want to basically evaluate the economic performance and for the conventional plant, and also not only the economic, let me tell you the total altogether. Economic environmental performance for the use case scenario or combination plant. And then we do the another analysis, which is the economic and environmental analysis, integrating the any project specific innovation to the conventional plant. And we also perform the thermodynamic analysis with and without integration of the innovation. And we also perform the thermoeconomic optimization to optimize the plant efficiency cost effectively. And this will also reduce the environmental impact further. So these are the main analysis we perform in our DSS tool. And basically, most of the project content, as I mentioned, that there's use case scenario or use case plant, depending on the project requirements. It could be either ORC or organic ranking cycle plant or flash plant. So we use this plant to perform our analysis. And this is not basically only not aiming to the project, but this should, the stakeholders will be able to use beyond the project as well, or generic use. So there are three main modules I already mentioned. We have economic module, and in this module you calculate levelized cost of energy, levelized cost of heating, and levelized cost of cooling, depending on the application. And then other financial parameters such as net present value, investment rate of reduction and payback period. And for the environmental performance module, depending on the methodology, we are actually using the Impact 2002 plus methodology. And according to this methodology, we evaluate environmental performance indicators. Those are human health, ecosystem quality, climate change, resources. And finally, we evaluate a single score, which gives you the total environmental footprint for all of the indicators. And then we perform the thermodynamic module, and we perform evaluate the first law and second law of efficiency, power output. And obviously for project specific, any like for absorption chiller or thermal energy storage, we also calculate the coefficient of performance and some other parameters. I've just listed here only a few of them. So as I already mentioned, that you actually develop coating material, which is actually anti-corrosion and anti-scaling, and high efficient heat transfer materials, so that heat transfer coefficient of the heat exchanger increases, and therefore the overall efficiency of the plant increases, and with a lower cost, because when you were increasing the efficiency, transfer efficiency of the heat exchanger, that means you need a smaller heat exchanger, and that impact on your cost, a lower cost actually. So I just put, so initially actually the project uses some square plates to do the lab test for corrosion and scaling and for heat transfer coefficient, and then using, there are so many coatings, but who qualified as those coatings qualified as anti-scaling, anti-corrosion, and showed a high heat transfer coefficient. Those were selected to develop the Worsley plant and a lab scale Worsley plant. And so the lab scale Worsley plant were actually consists of both heat exchanger, which are coated with a GX coating, and another was the standard heat exchangers. So, and then the heat transfer coefficient was measured and compared, and we have actually very promising result was found in this lab experiment. And what we do, as we do for all of them, we just do the environmental and economic analysis for all this coating to see the sustainability of this coating. I missed any? No. Okay. So this is just on the left side, I think, yeah, it is the carbon savings. Basically, we consider a 15 megawatt binary power plant, and then we do the impact analysis, environmental impact analysis, and cost analysis. And then we replace the heat exchanger of this binary power plant using the geo-exported heat exchangers. And then we have found that the evaporator and preheater, they saved some carbon for savings for using the heat exchanger geo-exporting. But condenser really didn't show any, it's a negative result. And we're seeing the same on the other hand for cost analysis. The preheater evaporator is giving us some good results, but condenser shows a negative impact for thermodynamics. So there are some good results we obtained for the geo-exporting. Then the GeoSmart project here. In the GeoSmart project, actually mainly work on the flexibility, introducing thermal energy storage, and also it will increase the plant efficiency through the exploitation of more thermal energy that is available for this for this plant by integrating a scaling reduction system. And another one is again enhance the reliability of the SCC-based Warsi power plant by introducing a diabetic cooling system. And this project was successfully completed. And for this project, the two use cases was one was the high enthalpy flash type and replicated into power plant, where the thermal energy storage and scaling reduction systems were integrated to see the flexibility and efficiency increase. And other one was in the lower to medium enthalpy Warsi power plant in Insheim. And this plant is also integrated with the thermal energy storage and the diabetic cooling system for the flex to see the flexibility and also to increase the efficiency. And we do have some good results here for mainly for efficiency increase, I think. Yeah. The diabetic cooling system, scaling reduction system, they did a really great job in the GeoSmart project. So I'll just show you some one of the results for scaling reduction system. Though you cannot see that a big difference because but there's some improvement, obviously, we can say for climate change or carbon emission. But for LCOE, we see a very good positive result. LCOE was much lower when the scaling reduction system was integrated with the plant. So this is the economic impact for integrating the scaling reduction system in the Kilidare 2 power plant. SERI project actually developing a thermal energy storage. This is mainly to utilize the waste heat more efficiently and sustainably for the mainly for the renewable energy sources. And here actually there are three use cases. One of them were geothermal energy, and other I think was mainly the solar energy. And for SERI DSS, what we're doing, we are actually mainly doing both obviously economic and environmental analysis, and also developing thermodynamic modeling as well. So in the environmental impact analysis, what we are doing, we are evaluating the environmental impact analysis for all of the three use cases, and mainly obviously the geothermal case as well, and comparing it with the state-of-art battery technology. So this is just half of our, I couldn't fit it in here in the slide. Mainly the homepage of the decision support system tool, what we have developed for SERIN project. And this is just one of the results for environmental impact, which is comparing the Zorlu scenario, EG32 scenario with a battery. I can't see it, probably, is it lead acid? Yeah, it's lead acid battery. So you can see the impact, it's very good. It's much lower for the heater system. Right, got anything? I think we talked about a lot at nGEL project. So can I skip or move to the next, or want me to go? So in nGEL project, actually, basically, I already mentioned that from baseline to flexible tri-generation, that means using the energy with optimization by generating electricity, heating, and cooling. And the second concept is the solving the summer power drop problem. I already mentioned it that during the summer, SEC-based overseas power plant, their power dropped some certain percentage. I think Julie mentioned some percentage. I forgot the amount. But you can improve it by. So in that case, we'll be improving it by introducing an absorption chiller. So that's another concept. It's very interesting in nGEL project. Both of them actually. So in this project, we are developing actually the digital twin with decision support system functionalities which will actually analyze the sustainability of the nGEL technologies and everything. So and there are other as well. It's been, I think, my previous speakers already mentioned all of them. So let me just go straight to the digital twin thing. Yeah, so we are developing digital twin for the tri-generation works, the plant with decision subsystem, as I mentioned already. The digital twin will actually just replicate the behavior of the real physical plant within the project, including nGEL components integrated to the works plant performances, SEC performances, absorption, evaporation, thermal energy storage dynamics, ambient temperature impact. So during the project, we are mainly aiming to the nGEL concept, and because we need to demonstrate and validate the digital twin. But beyond the project, this digital twin will be able to, any stakeholders such as plant owners or any academic, they would be able to use these mainly for the ORC, the organic second plant, or any EGS plant, which is basically ORC. So this is not, so beyond the project, it will be a real digital twin so that people can use it in their plant, in the ORC plant and EGS plant. So that was our main aim to when finally we'll develop the digital twin. But currently we are demonstrating aligning with the and validating aligning with the nGEL. And this digital twin actually will be used for the within the project for dissemination activities to let the people know what we are doing in nGEL, and it's overall everything performance, the sustainability analysis, everything. People will know what they get to know about the nGEL project. Oh, I did mention all of that actually in previous slide. So in concluding remark, what we can, I already mentioned everything that what we do in DSS2. We analyze the sustainability for the innovative equipment and when they are integrated to the plant. So we see before and after integration, what is the impact, economic and environmental impact, is it negative or is it positive? And then also, we when the people, the stakeholders like plant owners, others, they can use the platform because there's a GUI and they can use on their own because each of the DSS tool have they can download the manual type document, so they will know how to use this tool. So they can use this tool on their own and can generate a feasibility report to learn about the nGEL system, and also they can use their own data to generate their own feasibility report using this tool. So that was it actually from my side. So thank you everyone for listening.
Okay, thank you very much for the nice three presentations. So basically, I really enjoyed it and it was very informative. Thank you very much.
Yeah.
And so based on the timing that we have, I would have one question myself that has came to my mind regarding the whole event of this year's European Sustainable Energy Week. And then I will try to address one or two, or maybe if we get time, more questions from the audience. So basically, my question would be to the three of you, whomever would be basically ready to answer that. The theme of this year's European Energy Week is to have a clean, secure, and competitive energy union. So it may be a broad question, but how can geothermal energy contribute to that, to a clean, secure, and competitive energy union?
I'm gonna take this one if that's okay, because that's right in where I work in my area. So geothermal itself is a self-sustainable energy type. So of course, if used responsibly and correctly in the best engineering methods, but geothermal energy is not supposed to be completely depleted unless the world itself stops spinning or there's an astronomical event again. But you can deplete the reservoirs. How that can happen? Of course, if you do not utilize the reservoir's fluid in a responsible or sustainable manner. That means by the time you are consuming the fluid to generate energy, you're also wasting some of it, and you are losing from the reservoir faster than it can replenish itself. But if you are responsibly using it, that means you have a sustainable, unending energy source right at the bottom of your feet, below your ground. And that will, of course, help compete against other fossil fuel or non-renewable fuel types. And that means you are not actually dependent on the other countries' help in terms of energy. And this helps create a sustainable, of course, and an independent energy market internally inside your union or inside your country. So that's, yes, geothermal contributes highly to independent or sustainable energy. And it's easy to say, as I explained in the beginning of the meeting, there is no other base load other than, of course, the biogas, but biogas or biofuel has to be replaced all the time. It's not like geothermal, it's not continuous. So there is no other base load power plant type other than geothermal that's also renewable and sustainable.
Thank you very much, Tuğrul. Kevin, do you want to add?
Just add to that, the geothermal is not affected by climate change, but it will affect climate change. So I think that's a very important and often overlooked thing about geothermal, because we're talking about El Nino, the super El Nino, which is going to heat up the surface of our planet. It's going to have different winds. So all the other surface-led renewable energy sources are directly affected by climate change.
Okay, we have from the physical audience one question actually. Hi, please.
Hello, Kevin. I have a question to you about geodrilling. So, that most of the environmental impact comes from the construction phase of the geothermal system, mainly from the drilling, right? So nowadays we are using the diesel powered drilling systems. So are you going to be, changing to that diesel powered drilling system to electrical powered drilling system? That will reduce the environmental impact, what I believe.
There is a great move towards electrification of drilling equipment. It's been in the oil industry for a long time now. Currently, unless we can hook up to the grid, then we have to have a feasible method of generating electricity. So we use diesel generators. So we've got the end product, which is electrified. The actual source of our electricity is still from hydrocarbons. I think that will rapidly change. And one of the things that we've looked at, and we've looked at a long time ago in Kenya, is we drill one geothermal well, and then the electricity, we put this wellhead generator on, and it actually powers future drilling. So that's one of the ways of doing it. To try and the other thing we're also looking at, which a lot of people overlook within the environmental impact and the carbon footprint, is we would like to move away from cementitious cementing of casings, because cement is probably the worst in the construction sector of carbon dioxide produce.
Thank you.
Okay, thank you, Kevin. I have one question here from the audience to Tuğrul, and the question is, how big of a HTS, high temperature geothermal storage system, can be built for geothermal systems, and what type of TES is recommended normally?
Wow, that's a great question. Thank you, but that's also a broad question, because that completely depends on how much you're planning to invest, how much power you're normally generating, or how much installed capacity you have, and for how long you want to store your energy. So if you're planning to store for a long duration, that means we will have to have, I think one of my colleagues from consortium can even answer that question even better, but I'll try to explain with my words. You need maybe an underground thermal energy storage in that case to store it for a long time, and you have large areas of storage. It could be liquid, it could be phase change material, it could be water itself even sometimes. And the capacity of the thermal energy storage, again, completely depends on what you are trying to store for. If you're planning to fight against the fluctuations of the daily life, that means about 10%, or if you're trying to go for the frequency reserve, for example, 5 to 10% of the installed capacity as a stored energy would be enough for a couple of hours. 2 hours is the usually the optimum amount, considering that usually frequency reserve is completely back to normal in a couple of hours. But if you're planning to do it for seasonal change, that's a completely new thing that you need to consider, which would have a lot of again, investment constraints and area constraints. So in our project, in nGEL project, we're trying to go for around 10 megawatt thermal energy storage, but right now we're struggling to achieve that because of the temperature constraints. So we are continuously redesigning to find the optimal point for the storage, but we may choose for now 6 megawatt thermal, and at some point in the future, if we plan to add a new ORC plant, that means we can also add a new heat exchanger for thermal energy storage as well. Since it's quite modular, if you plan that way, there is no limitation.
Thank you, Tuğrul. As we are running out of time, I would say that I will try to do 2 more questions, and in case there are any questions from the audience here and also online, you can always email it to us. So I apologize beforehand if I cannot address all. I will do a change of topic. I have been reading the questions, so I will go one for you, Mahfuza, and then I will end it with one for you, Kevin. Actually, how can digital technologies, AI and data scientific aspects basically support geothermal exploration, resource extraction, and operation of it.
The AI, yeah.
I mean, AI, data sciences, and digital technologies in general.
Yeah, okay. So by saying data extraction, mean you are meaning that is it the analysis in our tool or something?
No, I mean like geothermal operation and
Geothermal operation.
in general, and also exploration of it.
Yeah. Yeah, it could be trained. You need a lot of data to train the AI first, isn't it? So you have to have a collect or database probably to train your AI. Yeah. And then you can develop a predictive model for
But
different.
collectively thinking about, like, let's just say in an ideal situation, you have all the data, what would be the impact of these digital technologies?
Okay, so you were saying the digital technology now, yeah. Okay. So by saying digital technology, you mean the digital tool in our everything, in our tools and everything.
Well, but we can discuss about everything maybe, and specifically about the support systems that are.
Yeah,
We
obviously,
use in
that very
geothermal.
much, because we are sometimes actually struggle with the data and things to develop our modeling and everything. But mostly actually we struggle for environmental impact analysis and cost analysis, obviously. And if we can generate the data, a very good AI source, that would be really helpful for us to have a better impact analysis for our tool, obviously. Yeah.
I totally agree, and basically we are also
Yeah, of course.
involved with a lot of.
Yeah, and of course, and we always do a verification, validate the things with others, like standard plan data. So you can always validate the data with AI data. Then it is going to be completely reliable. Yeah.
Okay,
Thank you.
I think we have one more question. Thank you, Mahfuza. So, Kevin, I am unsure which one to choose, which one would be more interesting, but to me, like, do the drilling process that we are doing affect the surrounding geological formation, and what would be the ultimate effect of these drillings in the long term? Which a lot of people have concerns sometimes, so I think this would be a very interesting question.
Yes, I mean, the thing with drilling is that probably the biggest uncertain part of any geothermal project. It's like asking someone to walk blindfolded for 5 kilometers. We start from the surface. We're not ever 100% certain what's down there. Once we start drilling into the formations, we start changing things that have been at rest or whatever for 4.5 billion years or so, a long, long time. I think the biggest risk is when we start pumping fluids and that in, and we change the underground pressure regime, stress regime. There's always that possibility of either inducing new fractures or activating old faults. We've got methodologies now, downhole sensors, which can actually help us predict future seismic events, etc. So, but yeah, I mean, we have to be careful. It's one of those topics that we all agree to disagree on, but you have to be honest and tell the public that there is a likelihood or a possibility that there could be some changes subsurface which affect their lives on the surface. And like everything, if you plan for these events, they're never as bad as if you don't plan for them.
So there is time for one more short question, probably. Please, from the audience that are sitting here.
Okay, thank you, Shahin. It's a question to Kevin, and one of the audiences from online asked it. Which recent drilling technologies have had the greatest impact on reducing the cost and risk of deep geothermal projects? the second question is, and which emerging innovations do you expect to be the most transformative over the next decade? And then the third question is, as drilling continues to improve, what do you see as the next major bottleneck to scaling geothermal energy globally? Resource discovery, reservoir management, project financing, or something else?
Okay, I think probably the use of fixed cutter PDC bits, because of the way we are drilling into much higher strength rocks, and the fact that we can use conventional drilling rigs, drill pipes, etc. I think the biggest effect has come from PDC bits. Down the hole hammers, because I love them to bits, are still a very effective way of drilling deep holes, and people still do to this day. Cost reduction, though, it's always a difficult thing to quantify, because it depends how efficient the drill crews are. And as part of the Opti-Drill project that Shahin and myself were involved in, when you analyse all the time taken to drill a hole, the bit is on the bottom for less than 20% of that time. So it's not so much the technology as the actual implication of those technologies. And the second part of the question was, sorry?
Which emerging innovations do you expect to be the most transformative for the next?
Again, I think, once we start to look at the deeper, what we call the hot dry rocks with much higher temperatures, higher strength rocks, it has to be a non-mechanical drilling technology, because even the best of the PDC bits, they have a wear factor. So every time they wear out, you've got to trip back. And that's a very time-consuming and costly process. Over the next 2 to 3 years, I still think PDC bits will be the most cutting edge, excuse the phrase, before we develop all these newer technologies. Lasers looking very, very promising. The millimeter wave drilling that clays are developing, I mean, once they make the breakthrough, it's going to be a game changer. And the same with the plasma drilling. That again has got a really sort of promising future. It's just that we're almost there, but not quite. So, and I think investors are always going to go, can you guarantee me a hole in the ground? So they'll want well-proven technologies, and we'll see the developments. The other thing with a lot of the conventional technologies today, they're going to be temperature limited. So we need something else that can operate in these much higher temperatures.
So there was part, what would be the next major bottleneck for scaling geothermal?
Money. Simple. It's just a simple fact that we need people to commit money to these. The development of geothermal. Zorlu Energy, that they've put a lot of their own cash into things. Icelandic government. When you go around, the US government now are taking notice of geothermal as a baseload renewable. Here in the UK, it's all over the place. So yeah, it's money. Money is always going to be the bottleneck for almost every development.
Okay, so I think we have 1 more minute, and first of all, I want to thank the audience for attending our event, the people who are sitting here, and at the same time, the people who have joined us online. I'm really grateful for your attention, basically, and at the same time, thanking Mahfuza, Kevin, and Tuğrul for your really nice presentations. I really enjoyed it personally, and I wish everyone a really lovely day, and hopefully joining us within our next hybrid event, I would say.
Thank you.
Thank you.